Hi, I'm Julie Pierce, and this summer I worked on the low-temperature anaerobic membrane bioreactor treatment of domestic wastewater with Adam Smith, Professor Steve Scarlos, and Professor Ludgard Raskin. First, let me show you the system, and then we can go into all the other details of what we do. So, this is the anaerobic membrane bioreactor, and it's essentially a tank filled with biomass and 3 flat sheet membranes, and we pump it full of our synthetic wastewater. And whenever the level gets too low, a signal gets sent to the computer and the pump will automatically turn off. So we don't have to do that manually, which is nice. So once the wastewater is in the tank, the microorganisms that are in the biomass start going to work treating wastewater, like digesting different things that are in it. And then eventually they pass through the membranes and that removes the particulate matter. Once they're in between all the membrane housings, they get pumped out through these lines, and you can use the effluent to irrigate crops, or you could just return it to like a river or a lake, or basically like a body of water. The other feature is the sparging lines. I don't think you can really see them, but they're basically some other pumps that are connected to the bottom of the membranes in the bioreactor, and they flow gas out from the bottom of the membrane to keep it clear of too much biomass, because if it gets too clogged with biomass, it will get fouled and it won't, you won't be able to get any water through your system, and then it's no use.
Now, with any new technology, you have to make sure it's working properly. So for us, this means testing the quality of the permeate.
To check our permeate quality, we have the basic tests like pH and alkalinity. We also test the chemical oxygen band, or COD, to determine the amount of contaminants still contained in the permeate. The influent wastewater has between 400 to 500 milligrams per liter COD, and our goal permeate COD is less than 50 milligrams per liter. This is the COD in each of our permeates, one for each membrane housing and from the biomass in the reactor. We haven't been able to achieve our goal COD during operation yet, but there is a downward trend in our data that suggests we may be headed in that direction. However, clearly this is something we need to improve on in our operation. Our final quality test is volatile fatty acid, or VFA, concentration. VFAs are produced by the microorganisms in the biomass as they digest the contaminants in the wastewater, and are a major component of total COD. The total COD concentration in each permeate is represented by the solid lines, with the equivalent COD concentration from VFAs in the dotted lines. The difference between each curve is only over a few milligrams per liter COD. If VFA concentrations are reduced by increasing the biofilm in our membranes to improve treatment, we could potentially achieve our goal COD.
One of the most important questions in research is, why do we care? We already have plenty of wastewater treatment processes out there, so why spend the time and the money to develop a new one? While achieving the same COD removal as other water treatment systems, anaerobic membrane bioreactors have a few added benefits. The first benefit is the lower volume of waste created during treatment. Since our system is anaerobic, the microorganisms only get food from the wastewater rather than the oxygen. This means they don't grow as quickly, giving the system a high solid retention time close to a year.
When you dispose of the biomass, usually a little bit every week or so, it quickly decomposes. Instead of putting more trash into a landfill, you end up throwing out a pretty good fertilizer. Anaerobic membrane bioreactors also save you quite a bit of energy. Since they're anaerobic, they don't require aeration, so the reactor doesn't need to be mixed. A reactor is also running at 15 degrees Celsius, much lower than the typical 35 degrees Celsius, so you save on heating. In addition to saving you energy, anaerobic membrane bioreactors also make their own energy through the production of biogas. Biogas is a mixture of methane and carbon dioxide and can be anywhere from 50 to 90% methane. As the microorganisms digest the contaminants in the wastewater, they produce VFAs, which are then converted to the methane. If you capture this methane, you can use it like a natural gas. So, given enough biogas is produced from a high enough COD removal, you could even use the biogas to power your own reactor.
As of now, our system is running at about 90% methane in the brown and is producing anywhere from 400 to 200 milliliters per day of biogas in red. So our reactor is a bit too small to be able to power itself, unfortunately. We're still working on anaerobic membrane bioreactors, so what are we trying to improve? A very common problem with anaerobic membrane bioreactors is membrane fouling. A properly functioning membrane is mostly clear of any biomass, besides a thin layer necessary for treatment, and still allows clean water to flow through. When a membrane is fouled, however, it becomes clogged with biomass and prevents water from easily passing through. This results in a lower quality effluent, and if the problem continues for too long, can cause irreparable damage to the membrane. For now, we use sparging to prevent this, but we would like to decrease the need so we can use less energy. Another problem for consideration is dissolved methane in the permeate and within the bioreactor. As of now, there's no realistic method for recapture, so you end up flushing a significant amount of energy down the drain, as well as releasing a potent greenhouse gas into the atmosphere. In addition to continuing our work on our current bioreactor, this semester we'll also be setting up a new pilot scale reactor. If all goes well, who knows? We could be implementing the first full-scale anaerobic membrane bioreactor.